Today we have the pleasure of listening to Nick Ramsey, who's going to tell us about measures in simple theories.
Great. Okay, thank you. Apologies to the French people in the audience. I've given this talk once before, but that time was the first and only talk I've ever given in French. So actually now you'll be able to understand it rather than listen to my bad grammar. So this talk is measures in simple theories, but it's actually about two specific examples of what can sort of not work in simple theories. So you might hope, by analogy with what happens in NIP, that there's some nice theory of measures in simple theories. And for two natural guesses of what nice things you might expect to hold in simple theories for measures, we'll show that they don't. So these are counterexamples in some sense, but also I think it expands the view of what is possible in simple theories, and for that reason it's interesting. So this is a joint work with essentially everyone. So Artem Chernikov, Ehud Hrushovski, Alex Kruckman, Krzysztof Krupinski, and Anand Pillay. Not all of these people worked on this project at the same time. So, I think there were a lot of conversations that happened between two of us at any given moment, but okay, there are many co-authors on this project. All right, so let's just start with the definition. A Keisler measure over A is a finitely additive probability measure on the definable subsets using parameters in A in the variables x, say. So def xa is going to be my notation for the class of definable sets in the free variables x, where the parameters come from A. And okay, sometimes about the parameter, the variable context, so we'll omit that. And the starting point is the observation that you can think about a type over a given parameter set as a probability measure on definable sets over that parameter set. How? Well, you just say that the measure that you assign to a formula or to a definable set is 1 if the formula happens to be in the type and 0 otherwise. And because types are ultrafilters, this is a well-defined finitely additive probability measure on those definable sets. But very interestingly, we have lots of other nice examples, which don't necessarily come from types. So one example, which is sort of orthogonal to the context we'll be thinking about now, is that of Lebesgue measure in real closed fields. So if you work in the theory of real closed fields, you can define a Keisler measure over, say, the real numbers by stipulating that whenever you take a definable set in the real numbers, you can intersect it. Let's say it's in variables. You can intersect it with the unit cube of dimension n. Now, by Tarski's quantifier elimination for real closed fields, we know that every definable set in the theory of real closed fields is going to be cut out by equalities and inequalities between real polynomials. And so as a consequence, you know that all such subsets are measurable. So it makes sense to take this Lebesgue measure, and that gives you a way of defining the measure of any definable set. Now, a different example, which is more germane to what we're talking about, is that of non-standard counting measure. So if you have a structure which is given to you as an ultra product of finite structures, then whenever you have a definable set in the ultra product, that is itself, of course, an ultra product of finite sets. You can take the same formula and those parameters, and then you can evaluate them in each of the factors. And for each one of those factors, you can ask, okay, what fraction of the elements in my model are inside this definable set? So if we're given an x, which is in def m, so it's defined using parameters from the model, then it makes sense to ask how big it is in the factors, and the ultra limit of those real numbers will give you the measure of the set. Now, because adding works for finite numbers, this is of course a finitely additive measure, and because fractions like this are always between 0 and 1, it's a probability measure. So it's easy to check that this is a well-defined probability measure on definable sets. And one thing to note is that, okay, this works in any pseudo-finite structure, regardless of whether or not it is simple or not. But many of the simple theories we care about are pseudo-finite. So measures like this are fairly ubiquitous in the simple context. Okay, so because we're going to be talking about simplicity theorem, I sort of have to talk about forking and dividing very briefly. This is going to be one of the key notions. And I won't go too deeply into the grungy details of dividing lines and all of the combinatorial independent stuff, but I think it's important to have the definitions in front of us at least once. So forking and dividing are, a combinatorial notion of independence that was introduced by Shella in the course of classifying stable theories. And inside stable theories, it agrees with familiar independence notions, like in vector spaces, it agrees with vector space independence, and algebraically closed fields, it agrees with the algebraic independence, but it makes sense sort of in anything you look at. Now, the way you define non-forking is first you define what it is for a set to be small. So this is the notion of a dividing set. So a formula phi xa divides over A if there's some A indiscernible sequence. So you can think about this as a sequence of conjugates by automorphisms of the parameters. So you move the parameter around inside the model in such a way that the family of formulas you get by moving the formula along these parameters is uniformly inconsistent. So if it's an A indiscernible sequence, then for some K, it will be K inconsistent. So you can think about this as being almost disjoint. So what does it mean for a set to be small? It means you can move it around a bunch in such a way that you have very small overlap. Perhaps they're pairwise disjoint, but if you can't get that, then you get K inconsistent, and that's good enough to be small. If something has measure 1, then you expect that as you move it around, you're going to have lots of overlap, so it's hard to find disjoint families like that. All right, now a formula forks if it implies a finite disjunction of formulas that divide. Now, that just says, if you think about the set it defines, that a formula forks if the set it defines is contained in a finite union of small sets. So the sets defined by forking formulas are exactly the formulas that are in the ideal generated by the dividing sets in the Boolean algebra of definable sets over a given set, or over the monster even. Okay, so that is for formulas. And this extends naturally to infinite sets of formulas. If you have a partial type, then you say that the type forks or divides over A if it implies a formula that does. Or again, if you think about the solution set, if you look at the solutions of the type, that forks or divides if the solution set of the type is contained in a small set, meaning a forking set. All right, now this gives us some notion of independence. We read the symbol as A is independent with B over C, and we decorate it with the superscript F to indicate non-forking independence. And that just means that the type of A over BC does not fork over, that says over A, but it should say over C. That's a mistake. So it doesn't fork over C. And okay, what this means is that using the additional information you get from this parameter B, you can't trap A into a small set. So when you extend your type from C to CB, you of course have new things you have to say. So for example, you could be equal to B or you could be not equal to B. You could be in sets defined by B or you could not be in them. And what it means for A to be independent with B over C is that somehow you've said no to membership in all of the small sets. So this is some notion of a free extension. You take an extension from C to a bigger set, BC, in such a way that you don't put your realization into any small set. Okay, so this gives you a notion of generic extension, sort of like a very general notion of generic point of a variety, if you like. And it also gives you some notion of independence that generalizes familiar notion of independence in known examples. All right, so this notion can be used to cut out important model theoretic dividing lines. So if you carve up the model theoretic geography, oftentimes these dividing lines are described in terms of the behavior of the relationship of the relation of non-forking. So there's an old theorem due to Harnack and Harrington, which sort of tells you that you can think about stability purely in terms of the behaviors of independence relations with respect to that theory. So a theory is stable, which is what we're going to take this as our definition of stability, because I won't actually need anything about stability. So a theory is stable if and only if there's some notion of independence attached to your theory, which has this notion of extension. So you can take extensions, so it's symmetric, It satisfies finite characters, so dependence is always witnessed by a finite part of the tuples in question. It's transitive, so if you take a free extension of a free extension, that's a free extension. It's okay. It satisfies base monotonicity. So this says basically that if you couldn't learn more about A using CD than you could about using just parameters in B, then of course you can't learn more about A using parameters in D than you could using just parameters in C. Local character, so all of the essential information about A is always contained in some small set. And then the key one is stationarity. And this is the one that's really sort of characteristic of stability. And this is the one that says, okay, if you have a base which is sufficiently rich, so if it's algebraically closed, then if two things have the same type over C, and they're both independent with B, then in fact they have the same type over both B and C. So this says that basically up to automorphism, there's a unique way of taking a generic extension to a bigger set, provided that you're defined over a sufficiently rich base. So if you have such a relation, then it has to agree with non-forking independence. So, non-forking independence is given explicitly via some kind of combinatorial definition, but the right way to think about it is in the stable context, it just is some abstract relation that satisfies these properties. And essentially for every use of non-forking independence, most of the time you can work formally with these properties of the forking calculus instead of thinking about the definition in terms of formulas and sequences and disjunctions and so on and so forth. Okay, now the reason I give this definition is because this is extremely useful sort of in thinking about simple theories. So a theory is simple sort of by definition if non-forking independence satisfies local character. So this was the one that said, okay, if I take a type over a very big set, so maybe I have some huge uncountable set of parameters of size Aleph 17, and I take a type over that set, then still there is some subset of size bounded by the size of the language. So if I have a countable theory, then there's some countable set, such that I can view my type over the big set as a generic extension of the type over the small set. So that means that after I describe the element using some small set of parameters, all I have to say afterwards is that I don't put it in any small sets. Okay, it's not exactly that that's all I have to say because I'm not in a stationary context, but it's almost all I have to say. So, okay, that's the definition. But again, the right way to think about it is just that you have some independence notion which has nice properties. So this is the Kim-Pillay theorem. And that says that a theory T is simple if and only if there is some invariant relation on small subsets of M satisfying, okay, the same list as before. So extension, symmetry, finite character, transitivity, base monotonicity, local character. But additionally, there's one more thing, which is that stationarity has now been replaced with the independence theorem. And this is very technical looking, but what it says is basically that if you have a type over a model and you generically extend it to two different parameter sets, if those parameter sets are themselves independent, then those two extensions are compatible. And in fact, you can put them together in a way that's still generic over all of the parameters in sight. So it's a kind of consistency statement. You might have lots of non-forking extensions, unlike the stable case where there's a unique one. But as long as the parameters are independent, you can put them together. So it's a way of recovering a lot of the uses of stationarity. You have many non-forking extensions, but because you have this additional flexibility, as long as you can arrange for the parameters to be independent, they're compatible. And that's an extremely useful fact. So, and again, there's this punchline that whenever you have such a relation, it has to agree with non-forking independence. So again, you can forget about the combinatorial definition of non-forking and just think about these abstract properties. And for most of the abstract work in simplicity theory, working with the formal properties of this forking calculus suffice. Okay, so this is going to be simple theories for us. And here's Gabe's map. So, okay, here is all of model theory. And the highlighted part in the bottom is the class of simple theories. So the bottom left quadrant is all stable theories. So this includes many objects which are familiar to us, like algebraically closed fields and vector spaces, equivalence relations. It also includes things which are a bit more complicated, like separably closed fields, differentially closed fields. But we think about this as like the part of model theory that we understand the best. And the rest of model theory largely is developed as an effort to understand what aspects of the structure theory for stable theories can be salvaged in a less hospitable context. So simple theories were one of the first classes of theories just beyond stability that were explored. And there are a lot of nice things that we know. But if you look above the highlighted part, in the top left quadrant, this is the class of NIP theories. And NIP theories include things like the p-adics and the real closed fields. And it was early, it was early observed in the theory of NIP that measures, Keysler measures play an important role. And there are a lot of theorems that relate Keysler measures to types, or that explain how to understand groups in terms of measures, and measures are just super important in the theory of NIP. And if you read the NIP papers coming out, I don't know, maybe about 10 to 5 years ago, you get the impression that model theory had just made some horrible mistake. We spent years and years and years thinking about types, and all along the measures were just waiting there, sitting there waiting to be used, and probably we should have been thinking about measures from the beginning. But the moment you take a small step outside of the NIP context into an unstable world like simplicity theory, the tools that you have seem to disappear. So the motivating question was just whether or not you can say anything at all. So in the class of simple theories, we have lots of nice examples like the random graph and pseudo-finite fields, and these come with measures. So they come with this non-standard counting measures. So these measures are around. Of course, they don't have, the counting measure is not the only one. There are lots of measures, for example, types. But the question is, can you say anything meaningful about how those fit? So 1 and 2 are sort of like canonical examples for us of simple theories. But then in the third thing, I wanted to just say that there's also sort of a known method for generating simple examples from stable ones. So there's a paper called, I think, Generic Structures in Simple Theories by Chatsidakis and Pillay, which sort of shows how to take a stable theory, which say is model complete or eliminates quantifiers, and then to generically expand by adding new structure in such a way that you produce a simple theory, which is in general not stable. So the normal way of doing this is you can either add a predicate. So you just add a predicate to the language, and then you take sort of a generic structure in this language, or take the model companion. That's one way. Or you can add an automorphism and then make it generic. And if the model companion exists, then the theory you get should be simple. And the reason I mention this is because today, some of these constructions that we do are going to somehow be a more complicated variant on this idea that if you start with something stable and you expand with some random additional structure, then you expect the outcome to be simple. So that's going to be sort of a guiding piece of intuition for how our constructions work. So as I mentioned just a moment ago, really the question in the background is, can one say anything at all, which is non-trivial about Keysler measures in a simple theory? And okay, we know first off that there are lots of nice special examples. So we have the pseudo-finite examples, and in even nicer cases, you have these immeasurable structures, or where the measures are extremely well behaved, sort of highly constrained by formulas, and there's a lot you can say. Also, there's sort of more recent stuff. This is done by myself with Artem Chernikov and Ehud Hrushovski, where we show that if you take the randomization of a simple theory, then you get not a simple theory, but you get an NSOP1 theory. And there's some nice properties that you can say about how the measures work, because measures in the original theory will correspond to types in the sense of continuous logic and the randomization. And there's something you can say. So there's some nice structure. It's not, you can't interpret set theory in the measures on a simple theory. That's maybe the minimum that we can say so far. So those are nice, but limited in reach. And you might want to hope for more, relating measures to forking or relating measures to groups. And so that's what I'm going to talk about next, about the context for these questions. So if we have a global Keisler measure, meaning a measure defined in all definable sets using parameters from the monster, then we say it's going to be A invariant if the measure I assign to a formula is invariant under automorphisms that fix A pointwise. So another way of saying that is if I take a formula and I replace the parameters with something else that have the same type, then the measure doesn't change. So this is a natural notion. So it's invariant with respect to automorphisms, or invariant under changing type, changing elements with the same type. And this gives us sort of a notion of small set. So we say that a definable set X is universally of measure 0 over A if it's assigned measure 0 by every invariant measure over that set. So clearly, if you're assigned measure 0 for every measure, then you are in some sense small. So an example would be like a point. If you're a single point, then of course you have to be small with respect to every measure. That is invariant, provided that you're not in A. Or you're not in the algebraic closure of A, I guess. Okay, so this gives us some notion of small set, and then maybe a question you might ask is just how does it relate to non-forking? We have two notions of small set. How do they compare? So we have an implication going one way. So a formula that forks over A defines a set that is universally of measure 0 over A. So how does the proof go? It's very simple. Okay, now we know that a formula that forks is really, it defines a set that's contained in a finite union of sets that divide. So it suffices to show that dividing sets are universally of measure 0 because the measures in question are all finitely additive. So suppose you have a formula that divides and take a measure. Now, if the formula divides, then that's witnessed by some indiscernible sequence. So I can move it along some indiscernible sequence and get a family of instances that are inconsistent. So if the measure of the formula is greater than 0, then I can take some maximal k such that the first k instances still have positive measure. So maybe k is 1. So the formula has measure, I don't know, 1/2, but then if I look at 2 instances, it's measure 0 suddenly. So look at the maximal k such that it's, the measure is greater than 0. Then I can look at the first k, and then the second k, and the third k, and the fourth k inside my sequence, and those all have to have intersection measure 0 by invariance of the measure, and also the fact that k was chosen to be the maximal number of instances such that the measure is positive. So because these have pairwise intersection of measure 0, and the measure of each instance is positive, that contradicts the fact that I have a probability measure. Because if I take enough instances, then I have to be able to push the measure of the union of these instances up to something bigger than 1. Okay, so that's not so bad. Now the question is whether you have an implication going the other way, and that's something we'll talk about later. But before I get there, I want to just talk about the definitions for groups. So suppose you have a definable group, then we have a different notion of invariance around in the group context. So if we have a measure mu on G, meaning a measure defined on definable subsets of G, we will call this G invariant if the measure I assign to a set is invariant under left translation onto the group. The group certainly acts by left translation on definable subsets of the group, and so this makes sense. And we'll say that a group G is definably amenable if there's an invariant Keisler measure on definable subsets of G. So this is sort of the definable group analog of the notion we had before. All right, now let's talk about some examples. So the first one is that amenable groups are definably amenable. So what does it mean to be amenable? More or less, that means that you have some you have some finitely additive measure on all subsets of the group. Now, certainly, if you just restrict that to definable sets, it's still finitely additive, it's still a measure. So if you're abstractly amenable, then you're amenable in the definable category. And it's known that all solvable groups are amenable. So certainly, regardless of the model theoretic context in which you're working, if you have a solvable group, then you'll be amenable in the definable sense as well. But also, the class of all stable groups are definably amenable. So it's known just as a consequence of stable group theory that if you are stable, then G0 has unique G0 invariant generic type. And using that, you can sort of average to define a measure on the whole group. So if you take a definable subset of a coset, a G0, G0, you can translate back into G0 and just ask, is that in the generic type or not? So if you have a subset of a coset, then you can ask, is it a translate of something which was generic according to the unique generic type on G0? And if it is, then you assign it measure 1 over the index. And otherwise you assign it measure 0. And then given a general set, you just sum up the measures of the subsets of the cosets. So you take a set, you intersect it with each one of the cosets. Each one of those pieces is assigned some measure by the thing defined above, and then that gives you a measure on the whole thing. Okay, so it's easy to check that this is invariant, and that gives you a G-invariant Keisler measure. What's interesting is that this shows you that all stable groups have the property of being definably amenable, and that includes things like the free group on 2 generators by work of Sela. So that means that this is truly like a more general category than what we had before. Yeah, Artem is telling me that I lied because the index of G0 could be finite, but okay, locally it's going to look like this. So I guess you have to work with the local G0. All right, but more or less this is the idea. Okay, so here are the questions. So one of them is, do the universal measure 0 ideal and the forking ideal always agree? That's an interesting question sort of in general, but it's interesting to know, okay, what happens if you restrict to simple theories? And we have one implication. We know that if a formula forks, then it's universally of measure 0. So what about the other way? If something is universally of measure 0, must it fork? That's what we need to study. And the other one is, are groups definable in a simple theory always definably amenable? Okay, so we knew that it's true for stable. Is it true for simple? These are 2 questions. So we're going to show that the answers to both are no. So what do we have to do? We have to cook up a simple theory in which the measure 0 ideal differs from the forking ideal, or we have to cook up a group in a simple theory, which is not definably amenable. This will involve a kind of generic construction. And so what I want to do is just describe those particular theories for the rest of the talk. So here's our first construction. And I drew a lot of pictures of this. So this one addresses sort of a more technical question, but I think the construction is somehow more transparent. So I'm going to go through this one kind of slowly, and then afterwards we'll move to the group case, and we'll do that kind of quickly. So here's the situation. We have 2 sorts, O and P. So O is for objects, and P is for parameters, because we think about a particular formula that we want to be our formula that will not fork, but will still be universally of measure 0, with parameters coming from P and its object variable coming from O. So that's just for orientation. And we're going to have 10 unary functions. So you're going to have F1, F2, F3, F1 minus, F2 minus, F3 minus, and then G1, G2, G1 minus, G2 minus. So each one of these you think of as an element of a free group on 5 generators, together with their inverse. So you have all of that, together with a binary relation that goes from O to P. So it's like a bipartite graph. So just for orientation, the picture, I'm going to go back, but the picture looks like this. You're going to have O at top, which is like some objects. You have these green lines, which connect objects to parameters. And then at the bottom, you're going to have parameters, and there's some relations that are happening there given by the functions. Okay, so if you take an element of the free group on 5 generators, that determines a term. So think about H as like a reduced word in F1, F2, F3, G1, G2, and their inverses. And then you can obtain a term just by composing these functions in the associated way. So for example, the group element F1, F2 corresponds to the function F1 composed with F2 in the language on P. So what the axioms will say is, okay, F1 and F1 inverse are inverses of each other and vice versa. So this tells you that these functions are acting like automorphisms of P, or bijections on P. We'll have an axiom schema asserting that the associated action of F5 is free. So you have a free action. These elements give you a free action of F5, the free group on 5 generators on P. And the way you say that is that whenever you take an element of P, and a non-identity element in the group, then the element doesn't act trivially. And finally, we have this kind of funny condition which says that if I take an element of P and I look at its image under the Fs, and I look at the things that they connect to in O. So this is my notation. Rf1a means the solution sets in O to the formula Rx F1a. So I look at the objects in O that connect via R to the element Fa in F1a and P. Now, what that's saying is that if I take an element in P, I look at its three images, F1a, F2a, F3a, and they look at the things that these connect to. These are pairwise disjoint. But their union is contained in the union of the things connected to G1a and the things connected to G2a. So I have these three disjoint sets, and they're all contained in a union of two sets, which are given this way. Okay, so because the action of F5 on P is free, I can think intuitively that P breaks up as a kind of disjoint union of Cayley graphs of F5. So anytime I have a set and a free action of F5, I can think about that set as a disjoint union of these Cayley graphs. And so I'm going to draw the picture this way, and then I have some bipartite graph connecting O to P. And there are constraints based on the images of the elements about how objects can connect to things in P. So we'll describe those constraints. So before we get into the nitty-gritty, the goal now is to first show that this universal theory that we've written down has a model companion. So we want to take the sort of generic version of this theory. We will show that that theory is simple with trivial forking. And then we'll look at this formula, Rxa, for any parameter in question, and we'll show that it's universally of measure 0 but doesn't fork over the empty set. Okay. Cool. All right, so let's just think about the way that this could be hard. So suppose that I take an element, which I've called y here, and I say that I want to connect to it. I want to connect an object to that element y. Now, for example, that y is f1 of something, because the group is acting transitively. So if I take a y that's f1 of something, and let's call the thing that it is f1 of x. So if I apply f1 inverse to y, I get x. Well, okay, but that doesn't require transitivity. That's just because of a group action. So now if I apply g1 and g2 of x, then I know that the things that connect to f1 of x have to then connect to either g1 of x or g2 of x. Why? Well, because I was told that r of f1x together with r f2x and r f3x are all contained in r g1 of x and r g2 of x. What does that mean concretely? It means that if I put a plus at y, I have to put a plus either at g1 or at g2 of x, because these have to propagate. But then this continues, right? I mean, g1 of x is f1 of something. And if I apply g1 or g2 to that, I have to say yes to one of those. And I get a whole tree of implications based on these containments that I have to maintain. If I put something in R1, f1 of x, then I have to put something in either R g1 of x or R g2 of x. And then those things are f1 of something. So I have to put more things in g1 of that and g2 of that, or so on and so forth. So this propagates. And you might really worry that, okay, I have something with infinitely many implications. This is exactly the kind of thing that keeps you from having a model companion, because it's not the kind of condition that a formula can describe. So what we need is some way of getting around this problem. And there's a kind of combinatorial coding of this problem, which we'll study sort of abstractly. So if I get rid of the name f5, I'm just going to call it g from now on, and I have a free action of x, then as I mentioned, I can think about x as a disjoint union of Cayley graphs of f5. And I can use graph theoretic language to talk about that sort. So for example, I can talk about things being of finite distance from one another using the graph metric, the length of a path between 2 points. And if I have a subset, then I can talk about the ball of radius n around that set, which is just the union of the balls of the individual points in that subset in the graph metric. So this gives us the notion of a good coloring. So suppose you have a free action of G on X, then a subset of X is given to, let's call it D. I want to say what it is for a coloring on D to be good. So what does it mean to be a good coloring? It says that if I assign color plus to a vertex V, then for every I in 1, 2, 3, for the numbers from 1 to 3, there's some J such that if GJ Fi inverse V is in D, then I assign the color of GJ Fi inverse of V plus. This encodes our containment condition. So what does it say? It says, suppose you want to connect an element to V. Think this way. Suppose you want to connect an element to V. That V is F1 of something. Then in the G1 or G2 image of that something, you have to connect either to the G1 image or the G2 image. That's the containment condition in our definition of the theory. So this encodes the containment conditions that you'll see on the parameter sort. Now, on the other hand, we had this disjointness condition, which said that the Fi's are all disjoint. So how are we going to encode that? Well, suppose you want to connect to V. So that V is F1 of something. And that means you can't connect to F2 of that something, because then you would violate the disjointness condition. So if you assign V plus, then whenever you take I and J distinct, then if Fj of Fi inverse of V is in D, then you have to assign, that should say C of Fj Fi inverse of V is -1. It gets the color -1. And if D is the whole set, then you say that this is a total coloring. So this is very abstract. Let's look at the picture. So this is our containment condition. This is the first condition. So we were told in our theory that we wanted Rf1x, Rf2x, Rf3x to be contained in R G1, G2x. So that means if I assign plus to A is Fi of x. That means I have to say yes to either G1 of x or G2 of x. So what that means is I look at G1 Fi inverse of A and G2 Fi inverse of A, and I have to assign one of them plus in order to maintain this containment. Then we had this disjointness condition. So again, if I assign plus to A is, for example, F1 of something, Rf1x, Rf2x, Rf3x are supposed to be pairwise disjoint. So if A is F1 of x, then that means I have to assign no, I can't connect to F2, F1 inverse of A and F3, F inverse of A. So this says that our second condition really encodes the disjointness patterns that we see. I mean, the disjointness constraint that we saw in the theory. Okay, so just to return, we had this condition, and I know that this is confusing because you see like, okay, GJ Fi inverse is kind of hard to parse, but just remember that this is just a sort of combinatorial abstraction of the kind of constraints we had on when objects can connect to parameters. So I think my lemma disappeared. Oh no, I think I deleted it. Oh no, okay. Well, that's very frustrating. I had a slide which I think I deleted when I added this together. So okay, well, shucks. Yeah, I think when I copied this back, I erased my previous slide. Anyway, so there was going to be a slide which said the following thing. So you can compute a radius that you need to check. So suppose you have, I give you 2 n elements, let's say v1 through vn and w1 through wn. And I tell you a coloring on v1 through vn and w1 through wn such that the vi's get color plus and the wi's get color minus. Then if you look at the ball of radius d of n, and there's a way of extending the coloring to a good coloring on the union of those balls, then you can extend it to the whole free action. So you have a free action of g on x. you take a subset of 2n, then as long as you can extend your coloring to a union of balls of uniform radius, some function of n. In fact, it's it's a fairly explicit function of n. I think it's n times n plus 1 minus 1. Then you can know that you can extend it all together. And so what that gives you is this quantifier-free formula, which just says, basically, it says explicitly that there's a way of extending to the balls. And because the balls you can talk about using terms in the language, this is a definable feature. So there's a quantifier-free formula that says that if you take a size 2 n subset, you assign the first n plus, you assign the second n minus, then there's a way of extending that to the balls by the combinatorial lemma that I forgot to copy down. That means it extends to the whole thing. So it's consistent to add an element that connects the way you want to, namely it connects to the VIs and it doesn't connect to the WIs. And then you can axiomatize your theory, which says that, okay, if it's consistent to connect to the xi's and not to connect to the yi's, then you can. Then there's an element that does that. So this works just like, I don't know, the triangle free random graph. If you take 2n elements in the triangle free random graph, then as long as you don't create a triangle by adding the element, then you add it. You can add it. So here it's saying, as long as I can add an element which connects to these things and doesn't connect to these things, which is compatible with the containment and disjointness conditions, then I can add it to the structure. And once I've added those conditions, I've said everything I need to say. Okay, so the model theory of this structure is very easy to understand. So T star is the model completion of T. So in particular, it eliminates quantifiers. From quantifier elimination, you can quickly deduce that the only one types over the empty set are axiomatized by saying I'm in O or I'm in P. So that's all you can say. In particular, that means there's a unique one type over the empty set in P. So everything in P over the empty set has the same type. The only thing the type says is I'm in P. And also, definable closure in T is just closure under the action. So if you take elements in an object, the group doesn't act, so nothing changes, but you get the other parameters just by closing under the functions. Okay, so using all of this, we were able to describe forking. So A forks with B over A if and only if I have an equality between an element of the tuple A and some element of the definable closure of AB, which is not in the definable closure of A. So that means I have an equality between a coordinate of my tuple and something in the parameters. How many equalities like that can I prove? Well, only as many variables as I have. So in particular, that means that, okay, in one variable, I can only fork over a set of size 1, and that forking will come from an equality. That easily implies that I'm super simple of SU rank 1, but in particular, I'm simple. And it follows additionally that Rxa does not fork over the empty set, because this is not an equality. It doesn't imply an equality, which is easy to check. So because I know that all the forking formulas are equalities, this isn't one of them, so it doesn't fork. So now we get a counterexample to this question about universal measure 0 being the same as forking. So take your favorite parameter, call it A. So Rxa doesn't fork over the empty set, but we'll show it has universal measure 0. So why? Because there's a unique one type in P over the empty set, F1A, F2A, F3A, G1A, G2A, these all have the same type. They all realize the same type over the empty set. So that means if I look at R F1A, R F2A, R F3A, R G1A, R G2A, all of these have the same measure because the measure is invariant of the empty set. So if I take an invariant measure mu and RA has measure epsilon, then each one of these sets has measure epsilon. I was told that the RFIs are disjoint. So if I take their union and I take its measure, that has to have measure 3 epsilon. But they're also contained in the measure of G1A and G2A, the things that connect to those elements. So I have 3 epsilon is equal to mu of this union, which is less than or equal to the measure of RG1A, RG2A, because it's contained in it. But that is the union of 2 sets of measure epsilon that can be of measure at most 2 epsilon. So I've got 3 epsilon is less than or equal to 2 epsilon. So that means that epsilon must be 0. So I have a formula which doesn't fork, but it's universally of measure 0, and that means that these two notions are not the same. All right, so that's the first thing. Now we're going to move on to the second example, which we'll do sort of at lightning speed. So now we want to group. And the situation is we're going to expand the theory of algebraically closed fields, but we're going to think about SL2 as a sort. I mean, not formally, but intuitively, this is how it will work. So we're going to have 4 quaternary relations, thinking about elements of SL2 as 2x2 matrices, but you will really think about them as unary predicates on the SL2 sort. So, I mean, intuitively, you should think about them as unary predicates on the SL2 sort, but formally they're quaternary. So SL2 is our name for the definable group of 2x2 matrices of determinant 1, and that makes sense modulo the theory of integral domains of characteristic 0. And if I label these 2 matrices A and B, it's known that these generate a free group on 2 generators. So if I look at various conjugates of B by A, I get 12, different elements which generate themselves a free group. So what we're going to do is we're going to label those Aij as I ranges over the numbers through 4 and J ranges over the numbers through 3 in whichever way you like. So just choose some enumeration with these elements. So we'll call the group that these generate, so this free subgroup of SL2, will be called G. And we're going to treat these like they're individual constants in SL2. They're named by integer matrices, which are given by terms in the language, but we'll just treat them like they're built in the language. I mean, they are there. Okay. So our theory will say, you have the universal theory says, I'm an integral domain of characteristic 0. I have these predicates C1, C2, C3, C4. These are a partition of SL2. So they're disjoint and their union is all of SL2. And I have this axiom, which I'm going to call the coloring axiom. And what that says is that, okay, if I take an element, then for each I, translating my element by one of the J's, so for each I, if I translate the element by one of the Aij's, I have to land inside of the predicate Cij. Sorry, Ci. So for each I and each element X, I know that there's some J such that translation by Aij lands me inside Ci. It lands me inside the color Ci. And I think about Ci as being the things that get color I. And so I can identify each model as a pair, R and C. So R is an integral domain of characteristic 0, and C is a coloring, such that the things that get color I are exactly the things inside the predicate Ci. Okay, so again, our goal is as follows. We want to prove that T has a model companion T star, which extends the theory of algebraically closed fields of characteristic 0. We want to prove that that's simple. This is like a generic predicate on top of a stable structure, so this looks like should be simple. And we want to show that SL2 is a definable group in the theory, which is not definably amenable. Great. So where did my picture go? Oh, I think it got deleted also. I think I might have made a mistake when I compiled. Anyway, I had a very nice picture of what this looked like. But anyway, where did we go? Okay, anyway, so suppose you have a free action of the free group on 12 generators on X. Then again, we have a notion of good coloring. So this just, again, encodes this condition. It says that whenever I take an element X and X, then for all I, there's some J such that if I translate that element X by Aij, I get the color I. And again, we get a kind of bounding lemma. So this says, okay, if G acts freely on X and I take a subset of size n, then if I look at the ball of radius 2n plus 1 minus 1, and that extends to a good coloring, then I can extend to all of X. So so I should have said perhaps what it is for a coloring on a small subset to be good, but it just satisfies these conditions on everything in the subset. Okay. So the first observation is that it's easy to extend from integral domains to algebraically closed fields, because if you move from a small algebraic, or let's say from an integral domain to a bigger integral domain, then the SL2 in the bigger integral domain breaks up as a disjoint union of orbits under the action of G. And if you have a disjoint union of orbits, then of course on different components, there are no constraints. So as long as you have it defined on the structure you're given, then if you move to a bigger integral domain, there's no problem extending to a good coloring on the other stuff, on the other components. So it's sort of trivial almost to extend from an integral domain to an algebraically closed field. So we can assume a working modulo of the theory of integral algebraically closed fields of characteristic 0. And then we're going to come up with this notion of safety, which is going to sort of tell us when we can add a point. So by a curve, we'll mean an absolute irreducible
Nick,
curve.
just
Yeah.
to point out that it is 50 past.
Okay.
So,
Cool.
but feel free to take for
Yeah, so I'll take
5
like
more
2.
minutes. But
So I just want to get to the punchline of why this isn't definably meanable.
of course. But I was just
Yeah, no, I appreciate
telling
it.
you.
I appreciate it. Okay, so for us, a curve will mean an absolutely irreducible curve, and if you have some function on int4, then you think about this as telling you which indices get which color. So whenever I take a point, I want to know, can I, assign the ith thing the color j, something like that. So a curve will be called safe for C0 if for a generic point in my curve, coloring the point according to this coloring on the indices gives me something which extends to a good coloring. And because of this combinatorial lemma, which tells me that I only need to look at a ball of a certain size, this becomes a definable for a given curve. And because being a curve is definable in families, safety in this sense is definable in families. And that gives you a way of axiomatizing this theory. So you say that you're an algebraically closed field of characteristic 0, I should have said of characteristic 0, and it satisfies this condition that, if you're safe, then there is a point that gets the coloring associated to that coloring in the indices. Okay, now why is that definable? Well, you have to talk about families of curves of fixed complexity. And you know that this is a definable family, and then safety for them is definable in families. So, so this is an axiomatizable kind of thing. All right. Now, just very quickly, I want to say, okay, this theory is consistent, and it's the model completion of T. So you have elimination of quantifiers, and in fact, you have a description of types. Types just say the algebraically closed field type together with the isomorphism type of the coloring, and your SU rank 1. So now let's see why you're not definably amenable, and this will be the last thing I'm going to say. So towards contradiction, suppose you have some invariant measure on the group, on SL2. So by the coloring axiom, we know that if I fix an I, then all of SL2 is contained in the inverse image of AI1, AI2, AI3 of the color CI, because everything had to be either, either its AI1 image or its AI2 image or its AI3 image had to land in CI. So if I look at these sets, they have to cover the whole group. So what does that tell me about the group? Well, the group itself is assigned measure 1 because I have a probability measure on the group, but it's contained in 3 translates of CI, each of which must have the same measure. So I know that 1 is less than or equal to 3 times mu CI. I was arbitrary, so each one of these pieces has size at least 1/3. Now, C1, C2, C3, and C4 were a partition of SL2. So that means 1, which is the measure of SL2, is the sum of those pieces, and that means that its measure is at least 4/3, because each one of those pieces had measure at least 1/3. And 4/3 is bigger than 1, and so we get a contradiction, and that is all I wanted to say. So this gives us an example where the universal measure 0 ideal is different from the forking ideal in simple theories, and also a group in a simple theory, which is not definably amenable. And this tells you that the class of measures in simple theories were, well, I mean, there might be nice things to say, but at the moment it seems like we're finding more counterexamples than we are finding structure theorems. All right, so I'll stop there.